My name is Marco Faella. I'm the author of Seriously Good Software. As you can see, that's the book webpage here from Manning Publications. I'm a professor of computer science at the University of Naples, and I've been teaching a advanced programming language class for about 15 years now here in Naples. And from this class, I got the idea for this book. And tonight, well, it's night over here, perhaps it's afternoon over there, I will be giving you a preview of some of the content of the book. The idea for the book is the following. From my teaching experience, I noticed that in a traditional computer science curriculum, you tend to have a lot of in-depth classes about different topics in computer science, like algorithms and data structures and operating systems and so on and so forth. But I think what's lacking, at least I couldn't find a book that would present a global view over these topics and a way to compare and contrast these different topics. Particularly, I thought it would be helpful for junior developers or people studying programming to analyze all these different topics using the same example. So that's what I do in the book. I take a simple example, and in a minute I'm going to tell you all about this example. And I solve it many different times, again and again. And every time I try to optimize a different software quality. Now, what I mean by software quality is simply a property, a desirable property of software. Most of these qualities, as you can see from this slide, are commonly referred to as non-functional requirements. So you have efficiency that can be expressed in terms of time and space. And by space, I mean memory, of course. You have maintainability, usability, reusability, thread safety, robustness, correctness, and others. And these can all be seen as different forces that act on the programmer, pushing the programmer and the code in different directions. And of course, the poor working programmer also has to deal with deadlines. He has a limited amount of time, and usually this limited amount of time is a very strong force, and it's a force that goes against all of these qualities, because most of the time you're in a rush to deploy something, to show something to the client, and therefore you have little time to care about these properties or these non-functional requirements. And in the book I also deal with a special property, which is succinctness, basically writing the shortest possible program for a given task. And that's rarely desirable, of course. It's just a fun exercise that I think it would be fun to add, a fun addition to the book. All right, so this here is the summary of the book itself. And tonight we're going to have a quick look at these chapters highlighted in bold. So chapters 1, 2, 3, and 8. But as you can see, there's much more material in the book. Tonight, I won't be talking about space efficiency, reliability, and so on. So, let's start with the example that's going to be developed in the book and in this presentation over and over again in different times to optimize different software qualities. This example is based on the idea of a system of water containers. So the basic object is a water container. It can contain varying amount of water. And you have three methods interacting with these containers. You can measure the amount of water in a container with the getAmount method. You can add water to a specific container. And you can connect two containers with an imaginary pipe. And these connections are permanent. There's no way to remove a connection. This simplifies the implementation a bit, of course. And what's really important, is that whenever you add water to a container that's connected to other containers, that water that you're adding is going to be evenly distributed among all containers that are connected directly or indirectly to the one you're adding water to. Okay. So let me just check the chat in case anyone has any questions. All right. So in Java, that's the main language the book refers to. And in the book, you also find C# references. So it's mainly a Java book, but there's little notes about C# here and there to connect what I'm saying to C#, to the equivalent C#. And also most of the content, most of the techniques I'm discussing are actually applicable to any object-oriented language. Anyway, back to our example. The API that I have in mind for my water containers is the following. getAmount returns the amount of water in this container as a double value. Add water, you pass it an amount of water, and you're pouring this water into this container, but remember that this water is supposed to spread over all containers that are connected to this one. And then you can connect this container with another. That's it. That's a simple use case. So I can build 4 new empty containers, A, B, C, and D. I add 12 liters or gallons, whatever you prefer, of water to the first container A. Then I add 8 units of water to container D. Then I connect the first 2 containers, and then I print the amount of water into the first container. The situation right now is depicted here on the right-hand side. We have 6 in A, 6 in B, because I poured into A, but then I connected, and the simple action of connecting them automatically distributes this water among A and B. C is still empty, and D contains 8 units. Okay? So far, so good. Let's connect B to C. Now, the 12 units that were distributed among A and B become distributed among A, B, and C, 4 each. And D is unaffected. So if I print the amount of water currently in A, I get a 4. And finally, let's connect B to D. In this way, all 4 containers in one way or another are connected. Directly or indirectly, it doesn't matter. The water will still distribute equally among all of them. And so we get 5 each, because the total amount of water that I initially put into them is 20. Now, in this example, I first added the water and then I connected the containers. But in general, I have to support any interleaving of these 2 operations. And I can add here, then connect there, then add somewhere else, and everything should work all the same. Okay, so now I would like you to imagine your implementation of water containers. But your implementation should comply exactly with this API. Those are the rules of the game. All right, so let's compare what you came up with my first implementation. I call it a reference implementation, so it's kind of a baseline that's a compromise between different software qualities or different requirements. And later in the presentation, we'll see how it compares with more specialized implementations. So my baseline implementation goes as follows. In each container, I have two fields: the amount of water in this container and the group of this container, meaning the set of containers that are connected directly or indirectly to this one, including this one, because it's easier if it's uniform, if I don't have to treat this container specially. Okay, so let's have a quick look at the constructor, for example. I will just instantiate, whenever I build a new empty container, I will equip it with an empty set of containers as its group, and then I will add this container to its group. So this set of containers start with a single element inside, which is the container itself. Now, sorry, this is going to be probably the most boring slide in the presentation, so bear with me for 30 seconds and I'll try not to show any long block of code anymore after this one. So this is a simple implementation of connect to. What do I do when I need to connect this container with another container? Well, first I check whether they are already connected. This is important. Take a look here. To see if they're already connected, I simply check whether they point to the same group. So this check here is interesting. It's telling you that I intend to share these sets among all containers that belong to the same group. They're going to have the same set. They're not going to have different sets containing the same elements. They're going to link to the same hash set. So in this way, it's very easy to check whether two containers are already connected. They're connected if their sets, these group references here, are exactly the same. So if they're already connected, do nothing. There's nothing to do. The next 5 lines compute the new amount of water that should be in this container after the new connection. It's pretty simple. So I measure the size of the two groups that I'm merging. Then I compute the total amount of water that's currently sitting in those two groups of containers. So I'm connecting two containers, but in fact, by connecting two containers, I'm actually merging two groups. So in tot1 and tot2, I have the total amount of water in the first group before the merge, and the total amount of water in the second group before the merge. Therefore, the total amount of water in each container after the merge is going to be the sum of the two old totals divided by the new size of the group, so by the size of the merged group. And finally, with these 5 lines, I update all that needs to be updated. So I take this group and I merge it with the other group. Then I update the group pointer of all containers in the second group. So I let them point to the new group, which is this dot group. And finally, I iterate over the new group and I update the amount of every container in the new group. The new group is obtained as the merge, the union of the two old groups. Okay, not very interesting, just quite straightforward once we agree on these two fields, right? So it's just a consequence of having chosen these two fields. In a second, we're going to discuss whether this is a good choice of fields or not, depending on our objective, depending on our goal, depending on the software quality we are aiming at. But for the moment, I hope it looks like a reasonable choice. And I hope this looks like a reasonable implementation for the connection method. Now, let's focus on time efficiency and see whether we can improve on our baseline implementation. So a little introduction first. How do we deal with time efficiency? So step 0, first of all, we try not to deal with it. So first question you should ask yourself is, do you really need more speed? And you've probably heard the famous motto, premature optimization is the root of all evil, which means that programmers tend to optimize code too early or too much, even if it's not really needed. And optimizing for speed is not a neutral operation. So you're gaining speed, but you're probably losing on some other dimension, on some other quality. For example, you may lose readability. Your code may become harder to understand. So you should first ask yourself if you really need more speed. Then you probably should check the asymptotic complexity of your implementation. And I hope you've heard of this. It's a fancy mathematical way of talking and measuring the trend for increasing size of the inputs. So if you manage to improve your asymptotic complexity, your theoretical asymptotic complexity of the algorithm you're using, it's very likely that you'll get a practical advantage, a practical improvement as well. Then, after you have somehow achieved a good or optimal, hopefully, asymptotic complexity, you should switch to step 2, or you may switch to step 2, which consists of profiling and optimizing. By profiling, I mean you should guess, estimate, or measure 2 things. Usage profile. So how are your users interacting with your code, with your class, with your system? For example, in the case of a small class like our water containers, the usage profile boils down to how often do the clients call each method. We have 3 methods. They may be equally important or not, depending on the usage profile. And runtime profile, so measuring or estimating which methods actually take more time. Now, most people, when talking about profiling, they focus on runtime profiling. But as I'm going to show you in a second, in many cases, usage profile is also very important before you can, before you can optimize in the right way, optimize the right thing. When you do have this data, so when you do have an estimate of usage profile and runtime profile, then, only then, you should optimize, so you should refactor the most common or the most expensive method to gain the maximum speed. So you should focus your effort, your optimizing effort, on the method or the module of your system that's used more often according to the usage profile, and to the method or module that takes more time in practice according to the runtime profile. All right, back to our example. So let's start with the asymptotic complexity, and let's check the asymptotic complexity of the reference implementation. So, as you recall, we have a field holding the water amount in this container. Therefore, the getAmount method, which we haven't seen the code for, but it's trivial, just returns the amount that's written in that field. Therefore, the getAmount method is constant time, which in the big O notation is written as O of 1, which means its runtime is independent of the number of containers around, it's independent of the number of containers that are connected to this one, and so on. It's always the same, it's constant. On the other hand, connect to, which we've seen the code of, it contains all those loops, a couple of loops over all containers in the first group, in the second group, in the merged group. Therefore, its time complexity is linear. So it's proportional to the number of containers that are connected to this one, or more precisely to the number of containers that belong to the two groups that I'm connecting. And this we can write briefly as O of n, as linear. And finally, add water. When you add water, you also have to distribute it among all containers. So the add water method will also contain a loop over all containers that are connected to this one, so it's also linear. Now, question is, can we do better? And even before that, another question we should solve is, what does better mean? I think it's not obvious what better means because we have three different methods here with three different complexities. So, of course, if I can improve all of them at the same time, then it's better. But what if I can improve one while worsening another one, while increasing the complexity of another method? Is that better or not? So, let's see in practice what I mean by this. So this is our reference method, our reference implementation with its complexity. Now imagine we have an alternative one, another implementation where complexities are like this. So is this alternative better than the reference? Well, it clearly is, right? It clearly is, because I'm improving add water and I'm keeping the other two complexities the same. So this is better, and technically we can call it a dominating implementation. So this one, at least this time complexity table dominates this one, because on every row this table is better than the old table. So let's say that alternative one dominates reference. Now imagine we have alternative 2 where the getAmount method goes from constant to linear and the other two methods go from linear to constant. Now, none of these dominates the other because each alternative between these two improves on some method and worsens the situation on some other method, so they're incomparable. Which means that dominance is a partial order. And we can ask ourselves, what would be an ideal table? What would be an ideal implementation? Given that dominance is a partial order, we should be content. It's enough to have something that is not dominated by anything else. To have a table of complexities that is not dominated by any other implementation. And that's what this is what mathematicians call a Pareto optimal element, Pareto optimal time complexity in this case. Okay, now in our specific example, let's search for a Pareto optimal implementation by taking little steps. So first of all, we start from reference. Can we just improve add water to constant time? By changing the class, of course. You cannot just change the implementation of add water. You have to make a pretty substantial change to the class. And the answer is yes. We can do that by having a separate group object. Instead of just a hash set, we add a nested class called group, and each container will have a single field which is a pointer to a group object. And what does the group contain? The group object contains the amount of water per container and the set of its members. So basically we are moving the amount variable from the single containers to this other object, which is called a group. And then all containers that share the same group, so all containers that are connected, will point to the same group object. And this will make add water much faster because it won't need to iterate over a number of containers. It will just need to update the group object. I think this picture will help you get a mental model of what's going on. So in reference, you have in each container, this is the situation in the use case I showed earlier. So when you have 4 containers and the first 3 are connected, in the reference implementation, the first 3 containers point to the same hash set. And the hash set, in turn, points back to these objects. But the amounts, the water amounts, are located within each container. On the other hand, in this new implementation, which I'm nicknaming Speed 1, so it's the first speed optimized implementation, the water amount is sitting in the group object. And now the containers themselves, they only have a link to a group object. And then the group object contains a water amount, which is to be intended as the water in each of these containers, and a pointer to the hash set. And I'm sure you can see how with this architecture here, we get those time complexities. So add water is fast, is constant time, because it just operates here. Get amount is still fast, because it only needs to access this group object. And connect to is still linear, because you still need to merge these sets and then updates these amounts into a single group object. Okay, let's move on. Can we get this table of complexities? Remember that reference is like this, and this is what I previously called alternative 2. So can we add water and connect containers in constant time? This is the tricky part. I want connect to be constant. But I'm okay with raising the complexity of get amount to linear. Let's see how we can do this. We can do this with 2 tricks: circular lists and laziness. What I mean is the following. So first, notice that 2 circular lists can be merged in constant time. So suppose that A, B, and C are connected, and I represent this by linking these containers in a circular fashion. A points to B, B points to C, and C points back to A. It's a circular list with 3 nodes, and the nodes are the containers themselves. And D is isolated, and suppose that when a container is isolated, it has a next pointer which points to itself, as is commonly done with the circular lists. Now, if we simply swap the destinations of the red and blue pointers, we just swap these 2 pointers, we merge, we obtain a single list, circular list. So B was pointing to C and D was pointing to D. If I swap them, then B will point to D here, and D will point to C. So as you can see, it's a single list now. And that's the trick we're going to use to connect 2 groups in constant time. Now I still have to tell you how I'm also going to obtain constant time add water. And here the trick is laziness. So in other words, I'll implement these 3 methods as follows. Connect to, start from connect to. It will merge 2 circular lists, which is a very fast operation, and it does not touch the water amounts. It leaves them, it doesn't distribute water. Even add water does not touch water amounts except for the single container where I'm actually pouring water. So it will just add water locally. Okay, this is, for the moment, the water amounts are inconsistent. I'm adding water locally and I'm not distributing it yet. Then, whenever I call getAmount, I iterate over the group, I check the total amount of water, and I fix the amount of water in each container. So I'm distributing water as late as possible, only when the client actually needs the updated amount. This is a trick commonly called laziness. Okay, so before returning the amount, I distribute water. And this way I get this table. And this table is incomparable with the one for reference. A quick look at the implementation of this last version. So each container will have an amount field and a next pointer, and connect to when I pass another container, simply swap their next pointers. Okay. Now, clearly it would be great to do everything in constant time. And I think you realize, if you think about it, since there is this non-local effects, so containers are connected with each other, there is some non-local action. So when I pour water and then I ask the amount of water, at some point the object needs to talk to other objects. So for this kind of reason, we cannot do everything in constant time, but we can get pretty close to it. We can get pretty close to constant time using a family of algorithms known as the union find trees, using these data structures. These are a classical data structure for maintaining disjoint sets. And in our case, the disjoint sets are the groups of connected containers. And the way they work, I will not go into the details, I'll just give a very high-level overview. But the general idea is that you have a set of elements, and in this case they are the containers. And initially each element is isolated. And you have two operations. Union operation, given two elements, merge their sets. And find operation, given an element, obtain the representative of its set. So in other words, when you use this data structure, you merge elements into groups. Each group has a representative, and then you can iteratively merge groups with other groups. And after the merge, they will have a new single representative. So for example, if you want to check if two elements are in the same set, you call the find operation twice. It will give you two representatives. And if their two representatives are the same, then those two elements belong to the same set. Okay. Without going into details, let's just say that the trick to have an efficient implementation is to represent each set with a parent pointer tree. So with a tree whose nodes point to the parent and not to the children. If you use this representation, then the union operation consists in merging two trees, and the find operation returns the root of the tree. So the root of the tree is going to be the representative for that set. Now, what's the complexity of these union find trees? It turns out that the worst case complexity is that using union find trees, we can implement our three methods in logarithmic time. Now, this is, if you compare it with the previous tables, this is another incomparable table. Some things are faster, but some things are slower than the previous implementations, because a log n, a logarithm, is slower than constant, but faster than linear. It sits in between. However, this worst case complexity is not the best way to measure the complexity of union find trees. and let me tell you why. Let me remind you that there's three main ways of measuring the complexity of an algorithm or a data structure. There is the most common one is the worst case complexity. Is the complexity given the worst possible input or the worst possible use case. Then we have average case complexity, which is a probabilistic measure, is the average complexity over a given distribution of inputs. And then you have a third important way to measure complexity, which is called amortized complexity, which consists of an average complexity over a long sequence of operations. And you need to use amortized complexity. So in other words, that's the most appropriate way to measure complexity whenever you're dealing with algorithms or data structures that make investments, so that make some computational effort now to get some future benefit later. And that's exactly the case for union find trees. As a matter of fact, if you imagine, so speed tree is the implementation based on union find trees, and if you measure the complexity of a sequence of m operations on n containers, so a long sequence of operations, you get an amortized time complexity, so an average complexity for the whole sequence of operations of m, which is the number of operations, times a special function called the inverse Ackermann function, denoted by alpha, of n, where n is the total number of containers. Now, the good thing about alpha is that alpha of n is at most 4 for all n up to 10 to the 80. So 1 followed by 80 zeros. So in other words, the inverse Ackermann function is essentially constant. It's not formally constant, but it's essentially constant. You can replace it with the number 4, which is a constant, up to humongous numbers of containers. Therefore, the practical complexity of this sequence of m operations is just O of m, is linear in m. But this is a sequence of m operations, so it means that the average cost of a single operation is essentially constant. So for all practical purposes, the real average complexity of an operation on speed tree, which is the implementation based on union find trees, is constant. And if you're still not convinced by all this theoretical hand waving, in 2 minutes I'm going to show you the results of actually running, of performing a benchmark test of this implementation, and we'll see what happens. Before I run these tests, let me show you a picture taken from the book. So in this picture, I'm comparing a couple of implementations. Some of them we've seen it so far. They are reference, speed 1, speed 2, which is the one with circular lists, and speed 3, which is the one with union find trees. And then it also includes memory 1, memory 2, which are other implementations that you can find in the next chapter. We're not going to talk about them here. But you should know that these are the implementations that try to optimize the memory occupied by each container. And in this graph, you have space on the x-axis. And by space, I mean the average number of bytes per container in a standard scenario with the 1000 containers connected in 100 groups of 10. So a reference, for example, needs almost 60 bytes per container. It's very expensive memory-wise. And on the y-axis, I put the complexity of the slowest method of the 3 methods. So as you can see, reference sits here at 60 bytes per container, and the slowest, with the slowest method being linear. And speed 3 here, the one with trees, is a lot more space efficient, fewer than 30 bytes per container, and also the slowest method is essentially constant, because all three methods are essentially constant. And then you have different combinations. So for example, in a different chapter, we have a memory 3 and memory 4, which squeeze each container in fewer than 5 bytes. But on the other hand, they increase the complexity to linear here and even to quadratic here. You can find all the details in the book if you're curious. And finally, let's move to the final step in the time efficiency spectrum. Let's run some tests after all this theoretical analysis. For example, we could do these two experiments. First experiment, 20,000 new containers, so 20,000 invocations to the constructor, 40,000 calls to add water, 20,000 connect to, and so on. And this is the time in milliseconds. We have reference implementation takes 2 seconds to do all of this. Speed 1, 26 milliseconds, 500 milliseconds, and 6 milliseconds. Okay? This is what I get on my laptop. So as you can see, speed 3 wins with a huge margin over the others, particularly over the first one. It may be interesting to do a slightly different experiment, well, a quite different experiment, where I only do one final call to get amount. And this is the best possible scenario for speed 2. Speed 2 is the lazy implementation that delays all the operations, all the heavy operations, until you actually call get amount. And this laziness really pays out in this scenario here, because in this scenario, speed 2 manages to be even a little bit faster than speed 3. So this proves that the usage profile, how your clients are going to use your class, can have quite a big impact on your numbers, on your practical performance. All right. So summarizing, we're finished with time efficiency. Once again, first of all, before you dive into this deep and somehow complicated analysis, you should really ask yourself if you need more speed. Then you should have a look at asymptotic complexity of your algorithms, because those are going to have a big impact in general. And don't forget that there's various forms of asymptotic complexity, not just worst case, but also average case and amortized. And finally, after you are satisfied with your asymptotic complexity, you can move to your practical measuring and optimizing. Don't forget to pay attention to your usage profile, and don't forget that in some cases you can get an improvement by simply shifting the effort, the computational effort, from one part of your project to another project. So it doesn't just become faster. There's nothing becoming faster, but by just moving the heavy lifting to a different parts of your project, you can get a practical benefit depending on your usage profile. Okay. Let's move to the second and final software quality for this presentation. Let's switch to thread safety. So before talking about thread safety and applying thread safety to water containers, let me quickly remind you the landscape of concurrency support in Java. So at the base of it all, we have the Java memory model, which was overhauled. It was redone in Java 5 because there was a previous Java memory model, but it was found to have some problems. Then we have the low-level synchronization primitives and the thread-related primitives, which were all there since the beginning of Java, since Java 1. And these are the thread class, of course, implicit monitors, synchronized keyword, volatile keyword, wait and notify methods of the object class, and other facilities, but these are the main ones. Then Java 5 added a bunch of other classes which represent explicit locks, concurrent collections like blocking queues, for example, atomic variables, and task executors. So these are all abstractions that are based on these low-level primitives, but help you achieve thread safety and concurrency without dealing with these low-level primitives directly. Then more recently with Java 7 added the fork join framework, which is a framework for parallelizing certain types of jobs, of tasks. And Java 8 added a large library within the Java collection framework, which is the stream library. And in particular, since we're talking about concurrency, we are interested in parallel streams and also other additions like completable future. Now, this is a broad overview just to give you a little bit of context. On the other hand, in this like next 30 minutes, we're going to use the lower level. So we're going to use the things from the blue level here and a little bit of facilities from the next level. So we're going to use explicit locks and atomic variables as well. Now, what do I mean by a class being thread safe? A class is thread safe if multiple threads can use its objects concurrently with no client-side synchronization. So the client doesn't need to care about synchronizing and serializing these operations. So the class itself takes care of synchronization when that's needed. You may know that among the standard classes from the Java API, we have, for example, string buffer and vector, which are thread-safe classes, whereas string builder and array list, which of course are quite similar in functionality to string buffer and vector, these two versions are not thread-safe, just as an example. Now, when trying to achieve thread safety, you are somehow between a rock and a hard place, and because on the one hand you have to avoid race conditions. And what's a race condition? A race condition is when threads step on each other, they mess with each other's data, and so they end up in an inconsistent state. And this happens when you have missing synchronization. You have too little synchronization. On the other hand, if you put too much synchronization, or to be more precise, when you add the wrong type of synchronization, you can get into deadlocks, which is kind of the opposite problem. It happens when threads get stuck waiting for each other. That's because you have too much undisciplined synchronization. One more slide before we go back to our water containers and we try to make them thread safe. So before we do that, I think you should first decide what's the concurrency policy you're aiming at. So in other words, this is kind of the concurrency specification that you fix as your objective. And then you move to how to implement that policy, how to implement that specification. A concurrency policy establishes what can happen concurrently. And the rest, the other types of operations, must be serialized. So they must be protected by mutexes, locks, or some kind of synchronization primitives. What are some common concurrency policies in general, regardless of the context? You may have class-level concurrency, which means that what's concurrent is only access to different classes. So this is a very poor, very poor level of concurrency. Only different classes can work concurrently, but different objects of the same class cannot. They have to wait. So in other words, this corresponds to having one lock per class, and every method of every object of that class takes that lock, acquires that lock before it can run. So you have very little concurrency. Then next level is object level. So access to different objects is concurrent, is free to be parallel. This is a quite common level when you have one lock per object and all the methods of that object acquire that lock while running. Next, you may have, even if it's not so common, you could have method level concurrency. So access to different methods is concurrent. So you may have, in this case, you would have one lock per method of each object. And then finally, in some special cases, you may want total anarchy. Everything can run concurrently with no locks. Perhaps you don't care about race conditions. You're fine with them. Now, what about water containers? Where do we put them? What's the ideal level of concurrency that should be supported? And once again, this water container example is interesting also in this case because it's not standard. It doesn't sit cleanly in any of these levels because water containers are connected to each other. And so the natural concurrency policy is at the level of groups of connected containers. So if I'm doing something with the container, I don't want another thread to mess with all the other containers that are connected to this one. So what is concurrent is access to different groups. And that's in between the object level and the class level. So water containers, their natural concurrency policy sits in between these two levels. And this shows that this table of 4 levels is just a general guideline, but case by case you have to analyze your specific situation and see where your specific situation sits on this hierarchy, and sometimes it sits in between, as in this case. So what's the ideal concurrency policy for water containers? It's the following. If containers A and B are not connected, any method on A can run concurrently with any method on B. Because they belong to different groups, so there can be no race condition. There's an exception. If someone calls A.connect to B and another thread calls B.connect to A, even if A and B are not connected yet, these two calls should be serialized. They cannot happen at the same time because they are connecting the same containers. And any other pair of method invocations, no matter if it's a add water, a connect operation, or a add water operation, must be serialized. So in other words, we need one lock per group. And let's try to start from speed 1 because it's easier to work with. Let's start from speed 1 and try to make it thread safe. Now, what's the structure of speed 1? Containers have a single field, which is a group. And a group is a nested class with an amount field and a members field, set of members as a field. Okay, so as it is, it's clearly not thread safe. Let's try to make a thread safe connect to. Our first attempt is the following. At the beginning of connect to, we enter 2 synchronized blocks. The first synchronized block is on the group of this container, and the second synchronized block is on the group of the other container. There's a problem here. And the problem is called deadlock. I'm sure you can see it. So if a thread tries to connect A to B and another thread tries to connect B to A at the same time, they may go into a deadlock because the first thread acquires the first lock, then it may be interrupted and the second thread may acquire the other group because the second thread is acquiring the same two locks in the opposite order. And that's classical textbook deadlock situation. Okay, so we have to do better, and there's two general ways to prevent deadlocks whenever you have to acquire more than one lock. And this is the case here. First solution, acquire monitors while holding a global monitor. So add an extra global monitor. And two, acquire monitors in a fixed order. We're going to go with the second solution. In the book, you also find a discussion of the first solution. In this presentation, I'll go straight to the second solution. Let's make sure that we always acquire monitors in the same fixed order. How do we do that? We add a unique ID to groups. And then we will acquire locks in the order of their IDs. How do we add a unique ID to groups in a thread-safe manner? This is also a small problem in itself, but it's easily solved by a library class called atomic integer, one of those classes that were added by Java 5. So we add to the nested class group, we add a final ID field, which is initialized by calling increment and get over this atomic integer called ngroups. And ngroups is a static atomic integer, so there's a single one for all the containers and all groups. And this atomic integer class ensures that each call to increment and get is atomic. So it's not possible that two different groups will end up with the same ID. It's a unique ID. Then, in the connect2 method, we acquire monitors in the order of their IDs, or more precisely, in the order of the IDs of the two groups. And we can easily do that as follows. So first, we check if they're in the same group. Then we define references lock1 and lock2, and what they are, they're just aliases for the two groups, but ordered according to IDs. So what is lock1? If group ID is smaller than the other group ID, then lock1 is this group. Otherwise, it's the other group. So we're just sorting group and other group according to ID. The one with the smaller ID is called lock1. And then we enter these two synchronized blocks. And we do the usual merging operation. Okay, this is seems to be working in the sense that it prevents deadlocks, because if you always acquire locks in the same fixed order, you cannot get into a deadlock. On the other hand, there is a somewhat hidden race condition left. And the problem is the following. Assume we have three unconnected containers, A, B, and C, ordered by IDs. So the group of A is the smallest one, the smallest ID, then the group of B, and then the group of C. Now, what can happen is the following. Imagine thread 1 calls A.connect to B, and thread 2 calls B.connect to C. Pretty innocuous looking. Then thread 1 will acquire the lock of the group of A. Let's call it the lock of A for simplicity. And then the group of B. Now, it may be that thread 1 is paused or preempted by the scheduler, and the control passes to thread 2. Thread 2 enters its connect2 method, and it tries to acquire b.group, which is busy. So it gets stuck. The scheduler goes back to thread 1, and now thread 1 can actually perform the merge, and one of the steps of the merge is replace the group of B with the group of A. That's how groups work. So all containers must point to the same group after the connection. So it will replace the group of B, and then it will release here the old group of B, the old monitor, and then it will release the group of A. Now, thread 2 will resume while holding the obsolete group of B. So B.group, which thread 2 was waiting for, is now a useless object because it's not pointed to by any container, because that group has been replaced by A.group. So thread 2 will perform its connection while holding the wrong mutex, because in the meanwhile, the actual group of B has changed. It's a different object now. So this is a race condition, and it's not so easy to solve this problem. And the problem follows from the fact that the objects we are using as monitors change. I'm not saying that they change their state. It's actually that they become different objects. So I'm using as monitor A.group and B.group, but the object pointed to by B.group is going to change and become a different object after some operations. So it seems now that the only solution is to have full serialization. By full serialization, I mean we have a global lock, a single lock for the whole class. For example, you may want to use an explicit lock. There's a class for that. It's called the reentrant lock. So we have a static reentrant lock, single one for the whole class, and connect to performs the whole operation under this global lock. Okay, this is kind of weird, because if you're acquiring a global lock, then why are you also acquiring these smaller granularity locks? There's no reason. So actually, you can forget about the group locks and just acquire this class level lock. Okay, yes, it works, but that's class level concurrency. There's very little concurrency. Everything essentially is serialized now. So it's true, you have certainly no deadlock because you're just using one mutex. You certainly have no race condition, but pretty much you have no concurrency either. So that's not a great result. It's certainly not the concurrency policy that we were trying to achieve. To achieve our concurrency policy, we have to switch to a different perspective. We have to switch to lock-free synchronization. And lock-free synchronization is basically, in simple terms, it's attempting something multiple times until no contention is detected. So no race condition is detected. And as our friend here tells us, this is reminiscent, it's related to the CPU instruction compare and swap that you can find on most modern CPUs, but that's another story. So this is the solution. What is this idea in practice? What is this idea of lock-free synchronization? Is the following: you enter in Connect 2, you enter into a potentially infinite loop. Every time you try this loop, you acquire the two locks in the order of their IDs, as we did before. But then, once you have acquired those locks, you check whether those locks are still current, they're still up to date. So you check, now that you have the locks, so you have the exclusive access, you check whether lock 1 is still one of the two groups and lock 2 is still the other group. It may be in either order. It may be lock 1 is group and lock 2 is the other group, or vice versa. Or one of the groups has changed in the meanwhile. It could change between here and here, especially before you acquire the locks. This group pointer and this other group pointer could be modified between here and here. So once I have the locks, I check whether they're still current. If they are still current, then I'm safe. I made it. I can merge groups and exit. I'm the only one that has access to these groups. If this condition fails, then at least one of the two locks is obsolete, is old, has been changed. So I release both locks and I try again from scratch. So I go back to another iteration of this loop. And I try and I try and I try until I'm lucky enough that the locks I acquire are the real ones, are the current ones. That's the basic idea, the basic general idea of lock-free synchronization is always a structure like this, trying multiple times until no contention is detected. And I know this was a bit heavy, this sequence of versions, so let me try to clarify the path we did here. We started from speed 1. Speed 1 had no idea about threads, so it was absolutely not thread safe. We tried with fixed order locking, but we discovered the race condition due to the fact that the groups change. So the objects used as monitors change during a connect to operation. To solve this problem, we tried with a global monitor, and that's a safe, very conservative solution, but it limits concurrency too much. And finally, we ended up with lock-free synchronization. Let's summarize a couple of conclusions of suggestions about thread safety. First suggestion from this short presentation is, before you dive into the coding, establish your concurrency policy first. Then, if at all possible, avoid using non-constant expressions as monitors, because that's going to be a nightmare. Also, sometimes, as in this case, you may have a choice between full serialization or trying multiple times, also known as lock-free synchronization. And finally, as a global observation, you should really try to avoid low-level synchronization because it can easily get tricky. Okay, this for water containers was particularly tricky because we had this network of objects connected to each other. But also in other cases, it gets messy quite easily. So avoid it whenever possible and move to the higher level, a higher abstraction concurrency facilities like concurrent data structures, queues, streams, parallel streams, and so on. All right. Then, once again, this is the book where you find everything we said here and much more. We only touched on some of the topics in the chapter on time efficiency and thread safety, but in the book there's much more. There's space efficiency, two kinds of reliability, two different points of view on reliability, readability guidelines, generality, or also called reusability. Then we have a fun small appendix about succinctness, and we have the best compromise overall, the ultimate water container class, making a compromise between all of these good qualities. I'd like to thank my students at my advanced programming language class. They're doing their finals these days, so hi, maybe some of them are listening. I'll see you on Monday for your finals. And I'd like to mention briefly all the team at Manning. I don't know if you realize how much work goes behind one of these Manning books, it's a lot. And as you can see, that's a lot of people working on it to improve and get you the best possible book. And that's it. Thank you for watching.